Good morning. I think we can start. Hi, good morning. I think we can start our session. Okay, that's mean what we have this week, lesson 9, which means we do have 3 more lessons, 3 more weeks of instruction, including this one will be 4. Okay, and then the semester will be over. We will not, not everybody took the test. That means we will not talk about the midterm 2. Maybe next week or maybe tomorrow I can say like few things. But most of you took the test, and the average was good so far. I can possibly mute everybody. That's mean average so far is good, and I hope the review session helped, because I was trying to match the question on the test to the question that we solved during the review session. Okay, that means let's make nice and short session. This week we will talk about the limits at infinity, okay, which was not part of exam 2, and the connecting concept with limits at infinity will be the horizontal asymptotes. That means that's today. And tomorrow we will still talk about graphing, but we will combine all of the information that we have about the function, first derivative, second derivative, all of the asymptotes, and we will try to get the graph of the function. Okay? That means tomorrow will be just a few new things, but we will make the summary of everything what we learned in chapter 3. Okay, that means let's start. Do you have some questions? I know that some of you had a little bit of issue with examity, but most of us were went really nice and smooth. Everything was good. If you have question, of course you can email me, and please do not worry if you experience some problems. I will arrange something different. You will definitely take your test, because it's just crazy at the moment. Okay, let's do this. That's mean limits at infinity. We probably know some of the limits at infinity from oh no, we didn't cover. No. Okay, we know limits that are infinite limits, and we know, okay, let's see. We don't know limits at infinity. We will learn now. Okay, but what I have, infinite limits. Let me actually, hang on, I don't want, no, I don't want to show you. Okay, let's do this one. That means, for example, when we will look at the function, rational function, 3 minus x over 1 minus x, we can see that function is not defined at 1, but we can definitely find a limit. Yeah, and that's what I thought, that's what I meant. We remember this type of limits. That means we taking x is approaching 1 from the left and from the right hand side, and we checking how this function behaves on the left and on the right hand side at 1. Okay, and the easiest way and the more practical way is to use direct substitution. That's why I'm taking 1, substituting 1, and getting 3 minus 1, of course, 2, but then 1 minus 1. That's what was expected, because 1 is not in the domain, 0. We can't have really 0 in the denominator. We are not allowed to divide by 0. However, as soon as we see 0, we know that it's not really 0. It's just a small number, because x is not really 1. It's 1 from the left-hand side. Can you tell me the quantity, the one from the left-hand side? Remember, we are in calculus class, yes. yes, okay. Yeah, we can't say like 1 from the left, we can't say 0 or even half is far away. We have to be extremely close. Okay, 0.9999, I like this. Okay, that means 1 minus 0.999, it is almost 0, but can you tell me it will be positive quantity or negative? Positive 0, if I can say this way, or negative? It's positive because the number from the left is less than 1. That I can maybe indicate like that, 0 from the left, okay? And we also know, like arithmetically, a constant 2 divided by small number is a big number. And big number, of course, is positive, of course. A big number for us is infinity, okay? That means that's the infinite limit. Okay, and of course we know the conclusion. Let's finish that line, that as soon as we got infinity and x was approaching 1 from the left at this example, we can call the vertical line x equals to 1 a vertical asymptote, because this will be, we will not draw the entire function, but at 1 from the left hand side, function will go up, because we just calculated positive infinity. Okay, that means from the left-hand side and the other parts. Okay, and respectively, the second example, it will be also 0, but it will be more, I mean negative, because can you give me the number on the right-hand side at 1? 1 on the right-hand side? It's, yeah, 1.0000001. Yeah, we may have 1111. It's, yeah, it's still close. Yeah. But then when I take 1 and subtract this number, I will get tiny negative number, and then negative infinity. And this negative infinity is telling me that on the right-hand side, function will go down, yeah, in terms of graphing. That means that's good to know. Yeah, good to know the limits. Okay, but that's the vertical asymptote. Today's topic is a horizontal asymptote. That's what we have to do. We have to check how functions behaves at infinities. Or maybe not using the word infinities, we can say we will try to check the end behavior. Yeah? How function behaves at the end of the domain. However, sometimes the end of the domain is not infinity, because we may have like a finite number. Okay? That means checking end behaviors, but usually we think about the negative and positive infinity. That means now we will check the situation in the horizontal, yeah, manner. Okay, that means let's see. Yeah, that's what we will call end behavior. As x becomes really big, how the function, how curve behaves. Okay, and then, okay, I can show you this. I have nice settings. That means we can take the function, the easiest rational function, 1 over x. We do have a graph of 1 over x. We know that it's not defined at 0. And the infinite limits, which means the top of this slide is the old stuff. And 1 over 0, I didn't type it, which is okay. 1 over 0 will give me 1 over small number will give me a big number, but in this case it's negative. 1 over small number will give me big number. And as soon as my answer is infinity, I know that that value 0 is the vertical asymptote. Yeah, that's the old stuff. Okay, and finally, the new stuff. Okay. That means that's because tomorrow, as I said, we will combine everything. And one of the questions will be, please find a vertical asymptote of the function. Okay, that means now I'm just reversing. How can you find, if I will give you a function 1 over x, how can you find the vertical asymptotes? Do you think do you know what you can do? Yeah, everything is done. I'm just asking to kind of define whatever we see backwards. That means asking you what are the vertical or what is. Yes, Yatniel, that's actually correct. You have to find the numbers, the x value, that function is not defined. Mm-hmm. And then we have to find a limit, how function behaves. And as soon as we get infinity, that's important, then we can conclude, yes, at that point, function is not defined, and it's not defined in this way, has the vertical asymptotes. Because we also remember from discontinuity or from chapter 1, we may have a function that have a hole, yeah, like something like, let's say at 5. Function will be not defined at 5. Also, you will find the probably x minus 5 in the denominator, which means x function is not defined at 5. But then the limit will be not infinity. Yeah, that means let's say limit will be, I don't know, 4. Yeah? That means when you're computing a limit at the values that function is not defined and not getting infinity, that's not an vertical asymptote. Okay. But that's the way. Okay, now the other question will be find a horizontal asymptotes. Okay, that means horizontal asymptotes, you have to look at the function and just check the limits at infinity. How function behaves at the very, very large numbers in the positive and negative direction. So that's the notation. X is approaching infinity or X is approaching negative infinity, and the same function. And now we have just like arithmetically the opposite situation. I don't want to put infinity because infinity is not a number. I mean, I can do this, or I can be more, I can say 1 over big. But 1 over big number, of course, is a small number. 1 over big number is, of course, small number. Big is that infinity. But mathematically, I shouldn't use infinity as a number item in my equations, in my expressions. That means this is, of course, positive big and negative big. And we know we don't really have positive or negative 0. That means it's just 0. Okay. That means one more time, 1 over small number is a big number. 1 over big number is a small number. Okay, and this 0, now the other way, this 0, okay, is of course always the answer means is the y value. I mean, I can say this is my I can just simply write actually that y equals to 0, yeah, in both cases. It will be a horizontal, like limitation, horizontal asymptote. Horizontal asymptote. Okay, y equals to 0. That means now we can see as we're computing a limits at infinity, and if we getting a finite number could be 0, like in this case, that number is a horizontal asymptote. And this means that as x is approaching big numbers, we can see 1 over x, 1 over 5, 1 over 500, 1 over, I don't know, 1 million. The values they are never gonna be lower than 0 because they approaching 0, and that's the line. Or from the negative, it's below, of course, because it's negative values, but the same thing. That means the curve is approaching 0 on both sides, positive and negative infinity. Oh, too fast. Okay, that means now what is the important thing? Important thing is to have a function, and I mean any type of function, and find the limit at infinity. Yeah? We have to know how to deal with these infinities. But please remember, a constant number over big number, always 0, always 0. Yeah? Okay. Yeah, let's find out some patterns because that's what we need. Okay, and this is just like a definition. It's probably obvious. It's just the notation. Let f be a function defined on some interval, and then the limit as x approaches infinity of f of x is equal to L. And this means that the value of the function can be made arbitrarily close to L. Yeah, they are approaching L, and L will be a horizontal line, horizontal asymptote. And I think I typed the way how we say this, but we know. It's just, yeah, just. Okay, and then I think I have the same thing for negative, the same thing for negative infinity. Okay, that means as x goes to the negative infinity, also all of the values of the functions are approaching that horizontal line L. Because L is the value, horizontal, like a level, height, if I can say it this way. Okay, let's start computing. Yeah, that's just the definition of the horizon, which I just said this. If this limit is equal to L, that number L is simply a horizontal asymptote. Just, yeah, we will have this later, but just in case, we may have different limit, yeah, at positive infinity and different limit at negative infinity. Okay. Oh, actually I have on the other slide, but I can show you, because sometimes depends on the function. Let's say the limit at positive infinity is L, or I can use actually the value, because doesn't mean that has to be, let's say is 2, and maybe at negative infinity, okay, it's like -3. Yeah, we may have this situation. And now, what is also a little bit tricky, we know, I know that you like feel, you know what asymptote means. Asymptote means that is the line that we never intersect, and that's true. Yeah, that's true. But what is, like, where exactly? Since we testing like a end of the domain, the huge numbers, that's the place that we can't intersect. Which means function, when we will draw the function at positive infinity, function has to nicely like respect the asymptote and never intersect, don't even touch it. That means, for example, I can have, I don't know, I can have something like that. Yeah, and we can see at positive infinity, that blue line will go closer and closer, but will never touch this line, y equals to 2. And the same thing, yeah, I have to respect the asymptote at negative infinity. So let's say I will have a function like that. Okay? But what's happened, if this function is continuous function, we may intersect these lines, these dotted lines, somewhere like in the middle, easily. Okay, and we're not really like, let's say, oh, okay, too far, it's okay. That means you can see I did actually intersect here, and it's okay, that's okay. But I have to nicely respect the asymptote at infinities. Yeah? This is fine, because actually tomorrow we will try to get the graph, and then you will see, oh, actually we're intersecting. That's okay. Yeah? That's fine. And we have to just respect at infinities, because that's the definition. Yeah? This line is a horizontal asymptote at infinities. And then I have a few examples. Yeah, we can see the first one, the second one, the third one, the fourth one, the fifth one, and the sixth one. Okay, that's we can see that even the first one, asymptote probably is only at positive infinity, because I don't know exactly, but I think the function doesn't really have at negative infinity, because it's not respecting. The same second graph also has an asymptote at positive infinity, because it's respecting. Number 3 is quite weird. Yeah, we actually intersecting infinitely many times, but function is still tending to get closer and closer to that pink line. This is also an asymptote. Probably the formula will be crazy, some trigonometric parts. And number 4 looks like we only have an asymptote at negative infinity. Number 5 is also at negative infinity, because I don't see that function, the blue curve, respects the line as an asymptote at positive infinity. No, and number 6, the last one, actually has different. Yeah, I don't know. I will not draw that part because looks like it's asymptote at negative infinity, and I will not draw this part. Yeah, you can just draw like the wherever is the asymptote. But we can nicely see 2 and -1 are different asymptotes because we're respecting. And what do you think? What is the maximum number of the horizontal asymptotes that function may have? Or what are the possible numbers of the horizontal asymptotes? What do you think? We may definitely have infinitely many. Can you imagine like infinitely many horizontal lines? And how we can respect them? Yeah, I think it's 2. Because we can have different at negative infinity, different at positive infinity. We may have only 1, or we may have actually 0. Like polynomials, they don't really have asymptotes. They are approaching to infinity or negative infinity. That means 0, 1, and 2. 2 is the maximum. But now, can you answer this question? What is the maximum number of vertical asymptotes? This is yes, Yatnia, that's infinity, because we may have so many, like even the trigonometric function tangent. Yeah, we have infinitely. Yes, Robbie, yes, that's the tangent. We can have infinitely many, and it's still fine. We still have function. We're still respecting every single like definition. Yeah, but horizontal only 2. Okay, maximum 2. Okay, let's see how we can compute. That means I believe you confident with this formula. Yeah, I just put nicely like in the more rigorous way, but this is basically what I said. If we have 1 over big number, it's always small number. And the big number, big quantity, I can define like that, like x to the power of any positive number, x to the power of 2, x to the power of 3, x to the power of, I don't know, 5, 6, 7, but positive. Because as soon as I put negative, I have to flip the fraction, and then it's not good. That we can see. Numerator is not even involved with x, that means it's just a constant. Could be any number, 1, 2, 3, 4, doesn't matter. I just put 1. Yeah, but 1 over x to the power of 1, 2, 3, 4, 5, 1 over big number is simply small number. Yeah? That means when we have this type of function, we know that right away this limit at infinity is 0. Yeah? It's simply 0. And 0 is a horizontal asymptote, just to finalize with the asymptotes. Okay. Yeah, and the same thing, even if it's negative infinity, it's still the same thing, because this means that it's happening at negative infinity and everything is probably below the x-axis. Actually, no, depends on the r. Depends on the r, because if r is even, it's still above. But it's 0. It's still, function is approaching 0. Yeah? Okay. That's what we will do now. Let's look at more complicated rational function. But we will use this as a tool. Let's mean now examples. Example number 1. Compute the limit at infinity of the function 1 over x minus 5. What do you think? It looks like 1 over big number? Or not really? If it looks like 1 over big number, the answer is a small number, 0, that's done. Yeah, we don't even have to. That's actually what I would like you to do maybe after the session, but I still want to show you. Yeah, it looks like, because this is like, yeah, it's 1 over big number. Thank you. Thank you for typing this. It's, of course, x is a big number. Minus 5, it's still a big number. I can, subtracting 5, I'm not really changing my infinity. That means yeah, the answer is 1 over big number. The answer is definitely 0. Okay? But I will show you some arithmetic steps, but I you don't have to do this way. As soon as you know that this is 0, just put 0. Because what I will do, I will look at this rational function, and 1 is just 1. But denominator, this x is my leading term. Yeah? I will try to allocate the leading term, which is just x, I just did, and I will try to factor out. Yeah, I know, probably looks crazy, but just I just wanted to prove like algebraically. That means I did factor out x, and we can see if I will multiply back, x times 1 is x, x times 5 over x, I can cancel out x's, and I have 5. That means everything is correct. And now, because we remember that tool, what 5 over x will do at infinity, if x is big number? This function, 5 over x, 5 over big number, also goes to 0. Yeah? Because we know, doesn't matter if it's 1 over big, if it's 5, yeah? If it's 5 over big, if it's like 500 over big, always that big, always this fraction, this function will go to 0. Maybe saying really generically, like I mean in general term, when we have numerator and denominator, okay, and if the denominator is winning, yeah, like in terms of some calculation, later we will have like more stuff, but if the denominator is winning, always the answer is 0. Okay, that means we do have, did I say, okay, I did type 0, but we can see if this is 0, 1 and 1, I only end up with 1 over x, because 1 minus 0 is 1, I can ignore it, and 1, again, 1 over small number, 1 over big number is 0. Yeah, that means this is kind of like showing you algebraically, but as I said, for this such an easy function, you have to just say 0. Okay, let's look at this one. 2x minus 1 over 4x squared plus 5. And x, of course, is at infinity. That means what? First of all, what do we see? Because that's also important, and we will need this for calculus too. Yes, math. That's actually really important. I don't know if I think I type it. We do have infinity and actually infinity. Okay, and infinity over infinity. I just put this because it's quite important. It's 1. Okay, Rob is saying that we can ignore negative. Of course. Yeah, I can, yeah. That's me. Okay, I will explain. But do you possibly can guess what will be the answer? Okay, 1. Okay, do you think what I said? I said that if we have numerator and denominator, yeah, and they kind of do the same thing. This function goes to infinity and this function goes to the infinity. That means it is big number over big number. But do we possibly can like define who is winning? A function on the top or the function like in terms of growing rate or being faster, being at the higher level faster? I think the bottom, yeah, the bottom because of the x squared. Because when I square the number, I always will have higher value. That means when the denominator is winning, doesn't matter, always 0. Yeah, but okay, I think no, you said 1, which is kind of like because you see infinity over infinity, and you can say, yeah, this is infinity. Infinity is kind of the same. It's 1. But yeah, we have to be really careful because yeah, I didn't finish because I was trying to tell you one thing. We do have 7, and we call indeterminate forms. 7 indeterminate forms in mathematics, which actually this is calculus 2. If you will take the calculus 2 with me, we will talk about all of them. But one of them, and indeterminate means like kind of like undefined at the moment. Yeah, we can still maybe do something. That's indeterminate. And actually infinity over infinity is one of them. Okay, infinity over infinity. That's one of them. And that's the thing, that seeing infinity over infinity, we can't assume that this is like they are the same weight, they have the same weight. No, we really have to investigate, because yeah, the common mistake, sometimes it could be one, but we always have to investigate what kind of infinities, like which of this expression will be faster, will have higher value. Okay, that's definitely indeterminate form. We can't just simplify and say one. Yeah. But what we can do, I saw some, I think Robbie, and I mean everybody said good comments. Actually, I would like to keep this infinity. Let me write maybe on the side, because it's nice to see, you will remember. Okay, that's what we will do. We will focus on the leading function. That means this is my leading function, 2x and 4x squared. And I will take this and repeat the same process that I did in example 1. I will factor out. Oh, actually, I kept the constant. It's okay, because we can do either way. I can take just the leading function, not the leading term. That means this is the main function. It's okay. I could keep the coefficient also outside. Okay, that means x versus x squared. And let's see what's left. Okay? That means we do have 1 over x, of course, 1 over big, 0. 5 over big, 0. No question, because then we're not really battling infinity over infinity. Okay, and then x over x squared, we will cancel out 1 over x. I mean, one of this x will be gone. 1 over x also goes to 0. Yeah, because this we have a constant. This will also go to 0. That means the answer is 0. Okay, that's what we can probably make. I think I had more, but we can definitely make the conclusion. Okay. Oh, actually, I do have the first example. That you can see, and please, yeah, all of these blue loops, the red loops, you don't have to do all of this step. I'm showing you because I think I have to kind of prove this. But please remember, if you see infinity over infinity, look at the leading function, whichever function is. If the denominator has a higher degree, this means that function is winning. If the denominator is winning, always 0. That's mean now, can you tell me the answer for this question, for this limit? Limit at infinity, of course. 5x cubed, x squared, 1, 4. And we know through this algebra that the rest, any other terms, they are not really important. They will disappear. They will be gone. We only have to focus on the leading terms, because they will take a lead. Okay, x cubed versus x to the power of 4. Of course, I did algebra, you can see, but no, it's definitely 0. This will go to 0. This will go to 0. This goes to 0. This goes to 0. And x cubed over x to the power of 4 will stay. That's why you don't have to even do this. You can just look at the leading terms. And this is the conclusion. For the rational function, okay, if the degree is less in the numerator, which means denominator is winning, always 0. Okay. And in terms of the asymptote, of course, this will be horizontal asymptote, but we're focusing on calculation. And I do have, can you tell me this question? Of course, like if you will see this limit on the test, on the final test, you just, of course, yes, thank you. You don't have to do, it's quite nice, simple concept. Okay, the next set of examples. That means 0, we know when it's 0. Now let's look at this one. Example number 5, which actually should be 4. Okay. No, 5, because the 4th one was at the bottom of the slide. Okay, still limited infinity, but now 3x plus 5 over x minus 4. It's still infinity over infinity. If we look this way, it's still our indeterminate form. The top will be bigger. looks like, yeah, because of course x versus 3x, yeah, it's a little bit bigger slope. But what we can do, we can try to use our algebra. Okay? Did I type this question? Yes, I did type this question because I was probably without the 3. Let's actually find out the, I like to write this infinity over infinity. This is my leading function and this is my leading function in the denominator. And let's do the same. Let's factor out. Okay, that means I'm factoring out the same way like I did in the previous one. 3 will stay 5 over x, 1 was the coefficient, 1 will stay 4 over x. And we know that this goes to 0, this goes to 0, 1 and 3 is a constant. But what's happened? X over x. Yeah, that means what is the final answer? Oh, it's 1, it is 3. Because actually they are the same function. That means I will factor them out, and since I have product, I can cancel them out. And whatever stays in the parentheses, which in this case will be the ratio of the leading coefficients. And since the leading function were the same, theoretically nothing is winning. Of course, having an answer 3, I would say, like having the answer, how can I say, greater than 1. Yeah? Then I can think, oh, function on the top has a little bit like, it's a little bit steeper, it grows a little bit faster, but they are still like comparable. They still behave almost the same. That means theoretically at infinity, if I have function x or 3x, a little bit more slope, doesn't matter. They are comparable. They behave the same. Yeah? In terms of the growing rate, I can say like both of them goes to the infinity at the same rate. And why I'm making this like a final conclusion? Because I see the finite number. Always when the limit at infinity is a finite number, this means that the battle between numerator and denominator, like none of the function won. They behave the same. Okay? If the denominator is winning in terms of the degree, then it's 0. Okay? But if the degree of the polynomials from the top and the bottom is the same, we're just looking at the ratio of the leading coefficients. Yeah, nice and easy. What is answer to number 6? Limit at infinity, 2 minus 3x squared over 5x squared plus 4x. Oh, we have to be really careful. Ratio of the leading coefficients. Yes, that's how your instructor can get you. Yes, because we definitely have, we have -3 and 5. And we can see x squared. Did I type? I did type this question, but you can give me the answer right away. You don't have to do this algebra. I factor out x squared because that's the leading function, and x squared, we can see the same degree. The zeros are this and this. -3 over 5 will stay. Ratio of the leading coefficients. Okay, that means this is the conclusion. If the degree are the same, yeah, then the limit is always just the ratio, not ratio, just the ratio of the leading coefficients. And I believe I have an exam type question at the bottom of this slide. Yeah, nice limits. And really nice like concept to remember, yeah, because we will refer this quite often, and especially in calculus too. Yeah, the bottom, because it's infinity over infinity is the indeterminate form. Okay, let's look at this. Who can give me, get ready for, what is the question? If you will see this limit number 7 on your test, final test. Limit at infinity, 4x to the power of 4 plus 5, x squared minus 2, 4x squared minus 1. Okay, yeah, it is 1 because I didn't type, I think. what I always like, what I always doing, I'm looking at the leading term, and then theoretically the rest of them, I know that they will disappear. And then when I will distribute everything in the denominator, I will also have the highest power will be x to the power of 4, and it's end up to have the same coefficient, 4 over 4. Oh, 4 over 4, 1. 1, okay. Okay, that means that's the only way that I can try to trick you. Okay, but yeah, good, 1. Yeah. Okay, but let's keep working still on similar, okay, oh, hang on, I just wanted to still this. But now I will give you a little bit different still ratio of 2 items, but let's look at the items. Let's look at the function. Something like that. Yeah, this is also kind of like an exam type. Limit at infinity, x plus 2 goes to the infinity, and the square root of 9, x squared plus 1. What do you think? Do you have the feeling what the answer will be? You might think close, really close, because, okay, limit at infinity. This is my leading function on the top. This, like whatever I will do, yeah, because I can still factor out, I can still keep my square root, I can still do it, but these circles are the leading function. That means they battling between each other. The rest of them algebraically will be 0. Okay, that means I can write limit as x goes to the infinity. I can say x, and maybe I can do this way because I need product. And then I can also do this way, right? I can, because I can factor out, I can split maybe, I mean everything, let's say this way. That's more understandable. Okay, and this will be 1 because I factor out x. Rest of them will be 0. Yeah, like whatever, we know that this, all of them will be, everything else will be 0. I factor out 9x squared, and then this will be 1. That means now we can see, I can only say that I have x on the top, and I have 9x squared, because when I have product, I can actually what I would like to do this way. Okay, like because I can keep the square root. As soon as I have product, I can split for 2. Yeah, for 2 roots. Okay, that means that's the battle. That means, what do you think? It's close. I think math makes small mistake, small arithmetic mistake, because square root is giving me square root. Yes, square root of x squared will be x, and square root of 9, it will be 3. X and x, the same function, the same degree. 1/3, 1/3 is the answer. Yeah, that means because of course I did some algebra a little bit short. I make the shortcut, but it's still correct. But let's look at the circles that I did at the beginning. X versus square root of 9x squared. We can just simplify. We know that this will be 9x. I mean 3x. X versus 3x. That's what I had at the end, and it's 1/3. But one thing is important, extremely important, because what I did simplify something like that. Square root of x squared, and I did say easily, yeah, x. And this is true if and only if the quantity x is greater than 0, is positive. In our case, we have to see that x goes to positive infinity. Because if this quantity, okay, if this quantity x is actually negative, I can't just say x. Yeah, because we know square root, the output is always positive. That means this is the only tricky part that we have to be extremely careful. Then that quantity x is actually negative, then I have to put extra negative to make it positive. That means as soon as x is approaching negative infinity, this means that x is negative. Then this will be the simplification. Okay, extremely important. Yeah, that's the definition. Because normally I know that we will, let's say, -5. Okay, square root of -5 x -5 squared. I can't just copy -5. Yeah, that's wrong. That's what I am saying. I can copy this -5, but I have to put extra negative. Because I will get 25, square root of 25 is actually 5. But using that exact quantity, I can copy, but extra negative. Okay, that means this is the only tricky part when we will see square root expression, even roots expression. Okay, let's look at this. Oh, I did type it. Oh, where is my, hang on, where is my pen? Oh, why I don't see eraser? Okay, I will just erase this. Oh, something is wrong with my. Okay, one second. Why my pencil? Okay, let's keep working. No, I need a pen, not a eraser. Okay, let me do this way. Okay, now I see the pencil. Okay, now I have the next example. Can you tell me the answer right away? Limited infinity at positive infinity, that means we good with this extra negative. Square root of 4x squared over 8x, right? Because we know, now we know 1/2 or 2x versus 8x. Yes, it is actually, I can say this versus this, 1/4. Okay, now number 10 is almost identical, but please note, okay, it's at negative infinity. That means I will still have 8x, that's not a problem, but this, because square root of 4, no problem, but square root of x squared will give me x, but negative 1/4, please remember. Yeah? And then I did type the definition. That's what I was trying to type on the side. Please remember, for the negative infinity, we have to respect the definition. Okay, question, yes. Yatniel, please, you may type or you may say.
So if 4 was a negative, then it would be positive 1/4?
We can't really have square root of -4. Okay. Okay, I know probably what you're thinking, because I can't really put -4. if I will put negative 4x squared minus 1, the entire quantity is negative. And I can't give you the undefined because we're just operating in the real numbers, no imaginary numbers. But what we may have, actually, I don't know if I can, you probably thinking about something like that, right?
Yes, something
Yes,
like
but
that.
yes. No, I can't ask you this way because this is still at negative infinity. Yes, okay, I know, okay. If you look at this expression, 1 minus 4x squared, we can still have this expression, but this expression is not defined at negative infinity. Yeah? If I will give you just the function and ask for the domain, you will tell me that, oh, this expression must be positive or equal to 0. And solving this expression, we will get what we will get, 1/2. We will get the interval between negative half and positive half only. That means the whole function, yeah, I know, it's you're trying to like adopt the whole algebraic arithmetic operations, but this blue function is defined only between negative 1/2 and positive 1/2, and I can't ask you how the function behaves at infinity. It will not make sense, which of course makes sense that square root of negative 4 is undefined. And we also have to actually exclude 3/8, which 3/8 is less than half. Oh, okay, such a complicated function because 3/8 will give me 0 in the denominator. Also, function is undefined.
Yeah, I was asking because on the right side it has the square root of x squared equals the negative x, so you have to have that negative there. So I wasn't sure if there was like a situation where you would have a x be a negative number and then it would make it positive, and if there was some sort of tricky thing to that too.
No. Of course, I understand, but
But it's not possible. Okay.
yes, it's not possible.
Yeah.
Which I perfectly understand. But what is also I know it's because you asking for the like more arithmetically, but also please, like this expression, even if I'm saying it's negative x, it's still positive, right? I know what you're asking, like the negative will give me positive because but even if I'm saying negative x, it's still positive because x is negative. An extra negative is giving me positive. But yes, I understand your question, and it will be not possible for this type of, let's look at my other examples. Maybe actually I did, but yes, no possible to give you function like that.
Thank you.
Yes, you're welcome. But okay, just in case, I don't know, just in case if you will end up having -2, of course, we will multiply together and the answer will be positive. Yeah, just in case, but no, not for this, not for this square root expression. But let's look, because I have more. This one, okay. I have these numbers, let's try. Now we have to be extremely careful. If you see the even root, okay, please do not play with like any negative or positive when you will see the odd root, because the odd root will go like it is, no problem. Yeah, I can simply, and especially the negative infinity, I'm saying. Yeah? But if we have an even root and negative infinity, we have to think. And I can tell you some of the examples are a little bit tricky. That means, let's see. Do you know the answer for number 11? Leading 1/2? I think it's 1/2, because we can, I just circled the leading functions. Cube root of 8 is 2. Cube root of x to the power of 6. I will divide 6 by 3, 2. And this is unchanged. Yeah, 1/2. Of course, I should keep limit, but it's okay, just to. Okay, now limit at positive infinity, then I'm not worried at all. Okay, what about this one? 1/4. I think it's 1/4 because the fifth root of 32 is 2. Fifth root of x to the power of 5 is limit at infinity, 1/4. Okay. Okay, what about now? We have negative infinity, we have to be careful. And we do have 16x squared, square root of 16 is 4, square root of x squared. Yeah, I have to be careful. Okay, because actually, what I did, I erase everything. Okay, I am crazy. It was 2 1/2. Okay, this one was 2 1/4. Okay, this one. I just hit erase everything. This is 4, and then I have this, and this is 2x. Rest of them is not important. You gave me the answer. Yes, I know. That means this one, okay, this one will be negative x, which actually it's still positive. -2 will be the final answer. I mean, this quantity, negative x, is still positive, okay? I do have another like conclusion, but I don't know, I don't want to. No, okay, let's leave it because, okay, maybe when we will have like a final review, I can show you like a different tool to test, but it's a little bit different to test only the sign of your final answer. Because you can probably imagine having question 13 on the test, I will give you the option like 2, positive, I mean -2, +2, maybe 0, maybe infinity, and probably 16, 8, and -8. Yeah, that's the typical like numbers that I can see that we may make mistake. That means you will probably know that, 2 or -2. Yeah, you will probably battle, you will exclude the other one. Yeah, but yeah, you will get this. Okay, let's see 14. Can you tell me 14? 14 will be square root of 9, which is 3, square root of x to the power of 6, 6 divided by 2 is 3, and x cubed, yeah? No problem. This is 3. Pause. I think okay, something is wrong because my, yeah, you see, but I can tell, actually I should maybe tell you. I don't want to confuse you because that's, yeah, you can see this is that negative x. Okay, now. And when I cube, it's still actually negative. Oh no, I have to make it bigger. Yeah, you gave me the correct answer. -3 is the correct. Okay, let's look at the next one. Okay, we do have 8x squared, no problem. We have square root of 16, 4, and now this one, because this one is interesting. Limit at infinity, limit at infinity. Yes, because this will be 4, and now I still have to say negative infinity. I mean negative x, like I did for the above problems, but now we can see square root of x to the power of 4. 4 over 2 will give me even exponent. That means just because of that being the even power squared, the negative will disappear. That means it will be +1/2. Yeah? It's still at negative infinity, but everything end up being positive. Yeah, that means that's another way, because we can see this one was cube, of course, negative stays. This one was to the power of 1, of course, stays. Okay. This is tricky. Yes. That's okay. What I can tell you, because I'm sure that everybody will get the correct, like a magnitude, correct ratio, like 2, 3, 1/2, because you can play with the finite numbers. How can you determine, I will use different color, that the final answer is negative, negative, or let's say positive for number 15? What you can do, everything what I did, like all of my steps, everything what I did between the first step and the last step, it's the definition of the absolute value. But we can also be a little bit like faster and maybe smarter, I don't know how to say, to even before starting the problem, let's look at this, I can try to compute or predict the sign of my final answer, just the sign. Yeah, positive or negative versus negative. That's, let's look at this. I have negative infinity. Yeah, function from the denominator, like 2 times x, it will be negative, right? Because it's at negative infinity. When I substitute negative numbers instead of 2, I will have negative infinity minus 3 negative. That means denominator is negative. On the top, I have x squared. I will square the negative numbers, and taking the square root is positive. Right? That means I have positive number versus negative. My answer, my final answer must be negative. But please, yeah, we can't be confused with the definition. It's something different. It's just testing the sign. And let's look at number 14. What sign will denominator give me? We have negative infinity, negative, thank you. And what about the top numerator? Negative to the power of 6 and the square root positive. That means we have positive versus negative. Arithmetically, my answer must be negative. And you even saw I make a small mistake, but I will always do the final check of the sign. And now let's look at number 15. We have x goes to the negative infinity, and what sign denominator will give me? Of course, positive, because we're squaring. And what sign will the numerator give me? Of course, positive. Positive versus, positive over positive. My final answer must be positive. That means this is, I think you will like it. That means you can actually do this way. You can kind of ignore the definition of the definition of the absolute value, like positive, negative, because that's different. All of the negatives that I placed between, that's a little bit different than my blue positive and negative. That means let's solve number 16. Don't worry for the definition. Can you tell me what will be the sign, just the sign? Okay, let's start with the numerator. We have x cubed, and x goes to the negative infinity. That means what is the sign of the bottom denominator? Negative. Excellent. And what about the top? X to the power of 6 is negative infinity, and then square root on the top of that, it will be definitely positive. That means what will be the sign of the final answer? Positive divide by negative, negative. But can you tell me now the quantity, the magnitude, the coefficient? We know that it's negative. It's square root of 4 over 4, 1/2, yes? And that's definitely correct. That means you may skip this. You don't have to do this way. If you like, this shortcut is, it's just here. And then you will never make the mistake, never. Because I know the absolute value, it's sometimes confusing. Oh, you can see, I did put negative x, but I will square, and the negative x disappeared. This one is cube, doesn't disappear. Yeah, it's, yeah. But testing the sign of the function, how the whole function behaves, it's perfect. Okay, oh, I know, oh, we should finish, but let's see, because I do have Okay, let me look at this. At this set. That means this one is definitely Mat 141. I took from your textbook. I don't know why they included. But 17, do you think you can tell me how function sine of x behaves at infinity? We know sine curve. Or it's getting closer and closer to 0. Sine looks like that. Pi, 2 pi, 3 pi. I can say that it's like 1, -1, 1, -1. And that means that's how it behaves. But of course, this is just my thinking. The limit is, yeah, it's oscillating, but we will say the limit does not exist as a one finite number. Yeah? We may think, yeah, we may, I mean, not even thinking, it's a fact, it's a true, but we're not writing. I can't say positive and -1. No. Okay, what about the other one? The other one, because function sine is continuous function, that means we can only focus on the limit of the inner function. It's fun. What is the limit of 1 over x at infinity? 1 over big number? Small number? What is sine at 0? Sine at 0 is of course 0. That's nice limit. Yeah, number 19 actually is another indeterminate form, but we will not. Yeah, no. We will not, because we will not. I could, but no. We will skip this limit. But I have I need like 4 minutes, 5 minutes. Okay, I hope you can stay with me. Because what we may have a limits at infinity that are actually infinities. And that means when we will see the limit at infinity and it's infinity, I just type a few examples, then in terms of the asymptote, we do not have a horizontal asymptote. That means let's take a function x cubed. Okay. Can you tell me what's the behavior of the function x cubed at infinity? And what is the behavior of the function x cubed at negative infinity? How function x cubed behaves at infinity? As x goes to the infinity really big, or can you type for me? We can think that we taking a cube of this infinity. It's of course even bigger infinity. Yeah. When I cube negative big numbers, I will have negative. Okay. And we can see this function goes to negative infinity, function goes to positive infinity. Yeah. That means this just means that limits at infinity are infinities. We may have this case. And I can show you 2 more examples of rational functions. We will skip this, and I would like you to tell me these 3 limits, and that's everything for today. Okay, that's rational function. That means we're getting back to our calculations, limits at infinity for all of them. But now let's investigate the leading functions. Now, who is winning? Numerator or denominator? 2x cubed versus x squared. Numerator. That means this is, of course, this will be the conclusion. If the numerator is winning, do you think what will be the answer? Always? Because we still using like the same idea. The rest of the terms are becoming 0. That means we will end up with, it will be always positive or negative infinity. Of course, we have to just add the arithmetic. We will end up with 2x, x goes to the infinity. The final answer is infinity. Okay, what about the second one? Who can tell me the answer for the second one? Have to be careful. That's my leading functions, and I only look at them. Is the answer positive infinity or negative infinity? We have to be careful. Let me just put negative infinity, positive. Okay, let's see. When I cancel out, I have 4x. And x goes to negative infinity. I know this is probably crazy because I can't really substitute, but we can see we end up with x. 4, positive 4 times x, and x goes to negative infinity. That's the reason that the answer will be negative infinity. Okay, and number 26, the last question for today, and looks like a nice exam type question because I'm trying to trick you. Look at all of the negatives and positives and tell me the final answer. This is the leading term and this is the leading term. And we are at negative infinity. I can copy this. Negative x squared, 20x. Okay, what is the final answer? Negative infinity. I can cancel out. I will have negative x over 20. X is negative infinity, yes. Because negative x and x is negative infinity, negative infinity will give me positive infinity, and of course, positive 20 is not. It's still infinity when I divide by 20, yeah? As we can see, the arithmetic is also important, and negative or positive infinity, like we have to check where we are. Okay, that was really nice, and thank you for answering all of my questions. And I hope I didn't confuse you. You actually asked a really good question. Okay, doing your homework assignment, and of course, looking at maybe at the textbook for the suggested homeworks. You will be fine with this. Yeah, with this. Tomorrow we will do multiple choice question, and I can show you because I will ask for the horizontal and vertical asymptotes. And of course, horizontal asymptotes, you have to compute limits at infinity. But when you getting infinity, it's just no horizontal asymptote. Okay, but you know how to compute the limits at infinity. I'm so happy. Okay, enjoy the rest of your day, and please join me tomorrow, yeah, because I love to have students in the classroom. I just love it. Okay, thank you. And thank you for some of you have the camera on. Thank you. And actually, even the microphone. Thank you.